Welcome back to our class on machine translation. Today we're going to look at evaluation. This is the most hotly debated topic in machine translation. If you find a group of researchers on machine translation talk to each other, you will notice after a while they're going to talk about evaluation. So in a way, it's a tough task, it's an impossible task, but it's also a task for which we actually have a workable solution that everybody agrees on more or less grudgingly, and that helped to make significant progress over time. So we're going to approach evaluation mainly from the question, how good is a given machine translation system? So we're mainly interested from engineering perspective. We have a machine translation system. We make some what we think are improvements, and then we want to know, is it better? So actually, even more than how good is a given machine translation system, we are even more narrowly focused on, is this machine translation system A that I just built better than the previous machine translation system B? It is a hard problem since machine translation doesn't have just a single right answer. There are many different translations acceptable, so ultimately the evaluation is about semantic equivalence and similarity. So we have a source sentence and you want to render a target sentence, and we have to answer this complex question of, is the meaning of the target sentence the same as the meaning of the source sentence? So we're going to go over first subjective judgment by human evaluators, and then automatic evaluation metrics, and we'll finish up with a quick view on task-based evaluation, which might be more realistic or more important for actual deployment scenarios. For instance, how much post-editing effort does it take to fix this particular machine translation into a high-quality translation, or how much information comes across, which is really the metric for a lot of the translator web page application of machine translation or translate a Facebook message. You want to know, did the intended meaning that the original author had put in come across to the reader? So here is why evaluation is hard in a nutshell. So this is from now already 20-year-old example from one of the first test sets that were created for machine translation evaluation in the modern statistical neural age. So these were Chinese news stories that were handed out to multiple translation agencies. Why to multiple translation agencies we talk about later. It's in the context of having multiple reference translations was deemed to be a positive. And you see here the different translations by the different translation agencies. So these are all professional translators, although some of them you could argue with not being super fluent English. Israeli officials are responsible for airport security. Israel is in charge of the security for this airport. The security work for this airport is the responsibility of the Israel government. Israeli side was in charge of the security of this airport. Israel is responsible for the airport security, and so on and so on. So they all basically mean the same. If you are like any other real professional translator, you would immediately say, well, some of these translations are terrible, and maybe you're going to say, all of these translations are terrible, only my translation is great. And then you think about for your own translation for another hour and say your own translation is also crappy and it should really be different or it's impossible to translate. So translation is a hard task, and it is still amazing how even a short sentence like this, and this is not a cherry-picked example, this is the norm. Even a short sentence like this, it's really hard to find multiple translators that come up with even one same translation. So there are two dimensions for translation that also are reflected in the evaluation of machine translation. And maybe it makes sense to evaluate machine translation differently in these two different aspects. And these are adequacy and fluency. So these are, another way to put it, is the two original goals of translation. One is adequacy. You want to bring the meaning across as closely as possible. But on the other hand, you also want to have fluent language in the output language. And these are a little bit in conflict for a translation problem, and maybe they should also be evaluated separately. So the original, kind of in the 90s, there were early machine translation evaluations on competitive systems, and they distinguished between adequacy and fluency. So human judgment here. So you have a human in the loop that has the machine translation output, and then has the source and or the reference translation. What is given to the human depends a little bit on kind of the real world constraints. If you're translating from a source language that is not generally known and it's hard to find annotators, well, why don't you just give them the human reference translation, and then it becomes a monolingual task. But on the other hand, if you have bilingual speakers, they probably get more accurate assessment of machine translation output by looking at the source. So you're given the machine translation output and the source and or the reference translation, and your task is to assess the quality of the machine translation output. So here are our two metrics. Adequacy. Does the output convey the same meaning as the input sentence? Is part of this message lost, added, or distorted? So did the meaning come across? And fluency. Is the output good fluent English? This involves both grammatical correctness and idiomatic word choices. So these are not cleanly separated. If you have disfluent output is incomprehensible, it's very hard to say anything about its meaning. But there are definitely these different types of mistakes. So here's a scale that was used. The text actually errors read was actually literally given to human annotators, and this is a scale that's given to human annotators. So adequacy, all meaning, most meaning, much meaning, little meaning, none. Fluency, flawless English, good English, non-native English, disfluent English, and incomprehensible. These are pretty terrible definitions, and it's not quite clear what the difference between most and much is on little. So no matter how much you try to define this more finely, you always are going to have some disagreement between annotators how to interpret these. Here's an example. So you have already, this is like a tool that we used in an evaluation campaign for a long time. So you have here the source sentence in French that I'm not going to try to read now. Here you have the human reference. Rather, the two countries form a laboratory needed for the internal working of the EU. So it's a bit EU jargon term. So I think these were the first evaluation where we actually took text from the European Parliament. So the two countries form a laboratory needed for the internal working of the EU. Not entirely sure what that means. And you have now translations of different machine translation systems. The first one is both countries are rather a necessary laboratory for the internal operation of the EU. And the human judge said, yep, that's the right meaning. So it's kind of interesting, are a necessary laboratory and instead of needed. Although the French here seems to have necessary in there. So that's a good translation, and it's also fluent English, as much as you can make fluent English out of the sentence. Both countries are a necessary laboratory at internal functioning of the EU. This is the second one where the annotator says adequacy is only 3 and fluency is only 3. And so on. So they have the other sentences as well. Here's an example of one that was named totally fluent, but slightly wrong. The two countries are rather a laboratory for the internal workings of the EU. So it's missing the necessary, for instance. Here's the definition we had. And yeah, so this is how actually a machine translation evaluation campaign were run for a long time with this kind of scaling and tools. So here, by showing translators 5 different translations from different machine translation systems that all needed to be evaluated in this scenario, um, give people a little bit more consistently how they judge the translation. So if there's one translation that is worse than another one, here it's easy then to give it a worse score, but if they're the same, it's possible to give them the same score. So there are several threes in either way. So this creates a little bit more consistency across systems. Okay, so this is a hands-on exercise that's a bit hard to do in an online lecture, but just think about it. Rank according to accuracy and fluency on a 1 to 5 point scale, where 5 is the best, the following sentence. It's a very short sentence. So here's the French, which is almost readable, and then here the English, the NSA affair emphasized complete lack of debate on intelligence. So what do you think should be the scores on 1 to 5 for the following 3 translations? The NSA case underscores the total lack of debate on intelligence. System 2. The case highlights the NSA total absence of debate on intelligence. System 3. The meta-NSA underlines the total absence of debates on the piece of information. So you have a scale from 1 to 5, adequacy and fluency. And you can now assign scores to these 3 different translations. Okay, let me just give you my opinion on these sentences. So the first sentence, I would say it has a fluency 5. It's perfectly fine English, at least according to my judgment, and also has the right meaning. The case highlights the NSA total absence, so that should really be NSA's total absence. So I can maybe give it a bit of a ding on the fluency, and still would say the meaning comes across perfectly. And the second one is that's very jarbled. I actually don't think that's very fluent at all. And then it gets a bit tricky with adequacy. So one interesting observation here is we now read the reference translation. Some of you might even understood the source. You read the other 2 translations. So we kind of really know what this is about. It's about the NSA and something, the debate underlines something about information gathering. So kind of things are there, but if you would have read this sentence completely out of context, you would have absolutely made no sense of it. It's also completely misleading that this is like on a piece of information instead of just apparently more about intelligence gathering. So I would say adequacy too. Okay, I don't know what you thought the scores were, but they may or may not have been different. Here's a statistical analysis of judgments made by different human annotators on the same set of sentences. So this is also from an evaluation campaign 15 years ago, where we look now only at adequacy judgments and see what kind of scores people gave. And this is one annotator. He basically never gave anything a score of 1, but otherwise was kind of normally distributed over kind of 3, 4 as the mean. This annotator here really like to give things a score 2. This annotator was much more positive, not as positive as this, but kind of similar. And this one here peaked at 4, never gave it 1. So if this is how annotators disagree with each other by using the scale, this obviously has some impact about how reliable these scores are. If you get a different set of annotators, if you just get a lot of optimistic people who just like stuff, um, you might get generally very positive scores, but if you get some pedantic people who just find fault in everything, you get fairly low scores. Okay, so this is something definitely when we think about evaluation, we need to be very keen about. So this is one of the key um, objectives of designing an evaluation metric is how much disagreement is there between different annotators applying the same standards, how much disagreement is there in the judgments. So this is something obviously that has been on the mind of statistics researchers and anybody that deals with survey answers and so on and so on. So we want to measure disagreement. And here is a formula that's often used, a kappa coefficient, that works for these kind of categorical judgments that we had here. So it's a 5-point scale. So just measures how often people give it the same score 4, and another annotator also gave it a score 4. It doesn't really give you any partial credit. If annotator says 4, one annotator says 4, and the other one says 5, versus one annotator gives it a 5, and the second annotator gives it a 1. This is treated as the same mistake. So the key here is the proportion of the times that the two evaluators agree. So they both give it the same score. And then is the proportion of the time that they would agree by chance. On a 5-point scale, there are 5 different assignments you can give, so that's 1/5. Okay, so here is the WMT 2009 evaluation campaign, how often they agree on fluency. So there apparently 40% of the time they agreed. By chance, it would have been 20% of the time, so the kappa coefficient is 2.5. While on adequacy, they agreed only 3.38, so 38% of the time. Same P of E. By chance, they would have agreed on 20% of the time. So this is a kappa coefficient. And yeah, you want that number to be high. There's some interpretations of what is an acceptable kappa coefficient is, but all this is a bit hazy. Okay, if you set up the task slightly differently, where you just ask, is translation X better than translation Y? So you just give them a pair of translations, and your only question is the translation X better than translation Y? Can people at least agree on that? One might just always give only scores from the range from 1 to 4, and the other one from 2 to 5, but given 2 translations, they both will may actually agree that one translation is better than the other. The setup we had earlier, where people were given 5 different translations at a time and meant to score it, can actually be converted in such a ranking judgment, where we just check, well, in this particular sentence pair, and here that both translations showed up, did they give translation X a higher score than translation Y? Therefore, they ranked X better than translation Y. So, so this is called sentence ranking, which can be done either on fluency and adequacy, but it could also be framed as just really the simple task: is translation X better than translation Y? And here, the P of E, since there are only 3 possible judgments, better, worse, or equal, is now 0.33, and this is how often the annotator agreed, and the kappa coefficient is higher. So this is a task that people can do a little bit more reliable, and therefore, for more than a decade after that, that was done as the method to evaluate machine translation systems in a competitive setting at WMT. Okay, more recently there has been revisiting some of this, and as I said, this is an endless debate. People come up with anything, and it's kind of interesting to point out there's a lot of debate about how to do human evaluation. So even the thing of saying, oh, let's just humans figure out, tell us which translations are better than others, there's not even agreement how to do that. So here are some lessons, however, from how to improve consistency. So one is to evaluate fluency and adequacy separately. So one way you could do this is to just people show just the translation with nothing else first and just said, is this a fluent sentence? So then they can read the sentence, or if they can't make any sense of it, if it's just garbled, they're gonna say it's fluent. So they don't need any source or reference to make that judgment. And then they're shown the reference or source, and then they can make an adequacy judgment. Another technique that has been shown to be really successful is this 5-point scale is just a really bad scale to gauge because nothing is really perfect. So 5, nothing is really terrible. So 1, and then some slight flaws. It's just one word a bit off. So is that a 4? Where another one is, yeah, it's mostly correct. Yeah, but it's more serious. Is it still a 4? Is it a 3? I mean, where do you actually draw the lines there? So instead, people were given a 100-point scale. So they were not actually asked to give numbers from 0 to 100, but they were given a ruler on a computer screen, and they can move the ruler wherever they wanted. So it's an analog ruler in a way. They didn't see that it was a discrete scale underneath. And with that, it's actually much easier to normalize the mean and variance of the evaluators. So if someone has an average of 30, another one has an average of 70, you can normalize that to saying, well, let's just change these curves so that they always have an average of 50, for instance. Another one is, so these are humans involved. Whenever humans involved, everything can go wrong, especially when you recruit evaluators with crowdsourcing services like Amazon Turk. You're always going to find some annotators who say, well, it's an easy task to make money. I'm just going to click randomly on everything. Nobody's going to check me. And how can you check against that? How can you just then discard all those judgments? So one trick is to show the same translation multiple times. So you give them 20 sentences to judge, one sentence at a time. And then at the end, you repeat items from earlier. And if annotators still give the same judgment, they're probably a bit more careful and can be trusted more. Another way is to also include the reference translation as a translation to be judged. Of course, that only works if you're showing the source in the translation. So you're showing the source in the translation, and sometimes you should show the source and the reference of translation. The human have reference translation, which should be scored really, really highly. So we can check for that. Another one is to include artificially degraded translations and just check if these actually indeed get worse scores than their non-degraded versions. So all these are ways to kind of check if annotators are doing a good enough job. Okay, here's some goals for evaluation metrics. And this is now also in transition to automatic evaluation metrics. So one obviously is a low cost. We want to reduce the time and money spent on carrying out the translation, so this has to be efficient. So we can't have people labor over translations for days, weeks, months before they give us an answer, because then when they're done, we might not be interested in the answer anymore because we moved on to other things. Tunable is an interesting one. So we want to optimize our translation system towards this metric. So if this is the metric that measures if we're doing good enough, we want to optimize our system towards doing well on this metric. So this is a very machine learning point of view. So we define a task and we measure the task, and basically how to optimize doing better on the task is to optimize on basically driving down the metric. And there are ways to actually feed that into the whole training setup. There's another one, meaningful. It would be good to have a metric that gives us some intuitive interpretation of translation quality. This is generally really hard. So the 1 to 5 scale, if you say on average, they gave it a 3.5. Well, it doesn't mean anything. Does that tell you, is this a good translation system? Maybe not. We're going to come to other evaluation metrics that are even less meaningful. So ideally, you want to have something like 10% of the words are wrong. And there are some metrics that do that. Consistent. So if you repeat the use of the metric, it should give you the same result. For automatic metrics, that's usually the case, but any kind of human judgment, that's a bit less certain. And then correct, which is a bit of a circular definition. So metric must rank the better system higher. How do you know it's a better system? Well, because the metric ranked it higher. If you have some other means to know that this is a better system, it should be ranked higher by the metric. So the only way to do this is in correlation to some other metric. Here's some other criteria of machine translation systems that go beyond quality of translation. So when you build a machine translation system, not only do you want it to be accurate, you also want it to be fast. So you want to have translations really quickly. You want to translate web pages on the click of a button. They have to, deal with size or just generally how resource use they have. Maybe you want to put a machine translation system in your cell phone. Integration is a real issue. How do you actually integrate that into an existing workflow? Does it have kind of a nice kind of properties of kind of accepting, for instance, translation requests on the fly and quickly responding to them, or is it just always just doing big bulk batch translation jobs that take forever and require specialized hardware? And another one is customization. So if a user has specific needs, just to give you two examples, maybe the user has this translation system and also says, okay, but here's my term of technical terms that I need to be translated in a certain way. So this word needs to be translated that way, and this word needs to be translated that way. So give me a machine translation, but follow those rules. That would be one way of customization. Another one that I came across recently in work I'm doing with a company on translation subtitles. They have to fit on the screen. They can't be too long. So the translation say you can only have 50 characters in the translation, so you can't have a longer translation. So can you kind of do this kind of customization? Okay, with these goals in mind, let's move on to automatic metrics. So what we really want is here a computer program that computes the quality of translations. So instead of going to human judges, which you already kind of spread some doubts about, we rather want to have a computer program that computes the quality of translation and does it reliably. It's low cost, tunable, consistent, has all these advantages. So the basic strategy, so you give them machine translation output, you give them a human reference translation. So that's the trick that makes the whole thing work. And the task is to compute the similarity between them. So instead of just basically saying, here's the source and here's the target, what do you think? We also say, but this is the target. This is a possible translation. So then it becomes a target side comparison task. So you have the English translation from the machine and the English translation from the human. And now it becomes just a similarity problem between these two English sentences. Okay, let's just look at work our way towards one of the metrics that was proposed. So let's just say we're just going to compare how many words we got right. So here's the reference translation. Israeli officials are responsible for airport security. And the system A has Israeli officials, an airport. And how many words did we get right? Well, we definitely get 3 words right, but it's not quite clear if this means if you have 50% of the words right or 43% of the words right. Why is that not clear? Well, what do you divide by? Do you divide by the 6 words that are here or the 7 words that are there? And what you divide by makes difference in if we measure precision or recall. And precision, we check on how many the system itself produced, so how precise it was in its prediction of words. So it was it produced 6 words, and 3 of them are correct, so that's 3 out of 6. Recall is how many of the words that it should have produced did it produce. So it should have produced these 7 words. So here we divide by 7. So these are two different metrics, and it's kind of obvious that you want to have both because it's easy to cheat either way. If you just measured on precision, then if there are any words you're not sure about, just drop them, don't translate them, only translate the part of the sentence you're sure about. So you're going to be precise on that. And if you want to do recall, well, just generate all words in the English language, and you're definitely going to hit all the words in the reference translation. So you don't want to, you can cheat that too, but you can't cheat both of them at the same time. So a typical way to combine this is F measure, which takes the product of them and then divides by the sum divided by 2. So in this case, this is 46%. Okay, here's another translation. System B says airport security Israel officials are responsible. And if you look closely at it, all the words are right, as indicated by these alignment links here in the middle. And so it has 100% precision, 100% recall, 100% F measured. But it's a pretty terrible translation. It's totally jumbled. But our metric that we looked at so far has no penalty for reordering. So this very simple metric of how many words did you get right actually doesn't work so well because it completely ignores word order. So what we could do instead is word error rate. This is actually a metric that's being used in speech recognition. So there we also take word order into account. So it's basically the minimum number of editing steps to transform output to reference. So you check, can you match the words? Or that costs no cost, or do you have to substitute words? Basically, for instance here, Israel, Israeli, or security and safety. Insertions, if there's one word added, and deletion, if there's one word dropped in the translation. And this then can be combined as this here. You count up all the errors, which are substitutions, insertions, and deletions, and divide by the reference length. One fun fact is that this might actually become bigger than 1 if you have an output translation that is bigger than the reference. How can you compute this? There's actually a nice algorithm that runs in quadratic times without optimizations and can be even optimized to be faster. That just tries to find the minimum edit steps. So let's walk through this here. On the left side, we have here the reference translation. Israeli officials are responsible for airport security. And then you have the machine translation. We're going to go through it word by word. So Israeli, yep, that matches. Officials, that matches. Responsibility, well, what's going on there? So you could say then, okay, that's a substitution with R. And then there's also this responsible. Let's count this as a substitution with of. Anyway, we have to kind of switch things out here to get to this point where we can then say, well, yeah, airport matches. Oh, and then safety doesn't match anymore. So we can compute this path here. The way this algorithm works is basically filling in this matrix and tricks and how can you reach each point in the matrix the best way. So at each point here, you ask yourself, how can I reach this point here? Well, I can just say it's a substitution from here, or it's a deletion from here, or it's an insertion from here. And it's always then 1 higher than that, so it would be either 0 plus 1, 1 plus 1, 1 plus 1, and the cheapest is 0 plus 1, which gives us 1. So this is how we can kind of move through this. Here's another example where you have reordering. So airport security, Israeli officials are responsible, which is just kind of this big word order problem. And this counts as a bunch of insertions here at the beginning, then a bunch of matches, and then a bunch of deletions at the end. Okay, so system A on the left here is deemed to be better because it has 4 versus 5 errors, so it has a good error rate of 57% versus 71%. Okay, so what error rate was initially proposed, but then not really further pursued. This kind of behavior with dealing with reordering is actually not happy. I mean, this airport security is not necessarily wrong, it's just the wrong place, and it just kind of makes it a really, really big mistake here, because he counted twice as wrong, once as insertions and then as deletions. So what was proposed instead, and it's been used since over 20 years now, is the metric called BLEU, also typically pronounced blue. So BLEU is French for blue, and BLEU actually stands for Bilingual Evaluation Understudy. Okay, it combines this idea of we want to check how many words we got right, but we also want to take care of reordering a bit by not just measuring precision for single words, but also for n-grams up to length 4. Since it's a precision-only metric, so we only check in the output of the machine translation system how much can be found in the reference, it has a brevity penalty that penalizes too short translations, which is this formula here. So it just checks output length divided by reference length. So you get a penalty if you're too short. You have 4 different precision numbers, one for single words, one for bigrams, one for trigrams, one for 4-grams, and you take the geometric mean of them. The metric was originally designed and is meant to be, and it still only really makes sense for doing it over entire test corpus test set. So like hundreds or thousands of sentences, not single sentences. It's very easy to nitpick that this is not a very good metric on single sentences, mainly because of this precision of 4-grams. Very few sentences, or many sentences may not have any correct 4-gram, and then you multiply here with 0, and that's not good. And it was never meant to be a metric for single sentences. There are definitely other methods that are better on single sentences. Okay, let's play this through for our 2 systems that we had here. So you have, in the first system A has Israeli officials, that's a 2-gram match, an airport, which is a 1-gram match, the rest is wrong. While in system B you have airport security, which is a 2-gram match, and officials are responsible as a 4-gram match. And then each 4-gram match also has 2 trigram matches in it, and 3 2-gram and 4 correct words, obviously. So in terms of precision, the first system here has 3 of the 6 words correct, 1 of the 5 bigrams, and none of the other stuff. Brevity penalty is 6 out of 7, so both translations are 1 word too short. While system B actually has all the words correct, all but 1 of the bigrams, 3 trigrams, 1 4-gram, same brevity penalty, so it gets a higher BLEU score on this. As I said, it's not meant to be on a single sentence, but we applied it just now to a single sentence. But keep in mind, this is not really, you want to do this over entire corpus of hundreds, if not thousands of sentences. So here's actually where our multiple reference translations, where we had our nice 10 different translations for the Chinese sentence at the very beginning, our example came from. So the authors of BLEU also advocated to use multiple reference translations. So that means if you have a phrase like responsibility of, it only has to occur in one of the reference translations to be counted as correct. So this idea is, yes, there are variety in translations. So how do we count it? Just have multiple humans produce different translations, and then we only have to match one of them. So that accounts for the variety of the translations. And that's a reasonable argument. Obviously, there's much more variety in possible translations, and you can have humans producing different translations. So it doesn't, you never actually account for the entire variety that is possible. So you still might have perfectly fine translations that still are not close to anything what a human wrote and therefore counts as mostly wrong. Um, so we generally have moved away from using multiple reference translations. One big problem is also these don't occur naturally. Uh, yes, we can get large corpora of translations, but there's very little material that is translated multiple times. So we always have to hire translators to produce multiple translations. And in practice, it has been shown that just having more translations is as good as having multiple translations. Okay, here's some other ideas that were then proposed. One was METEOR. That's a metric that did all kinds of stuff. I think its kind of innovative feature was flexible matching. So if we look at here, the sentence, the system says, Jim went home, and the reference says Joe goes home. Well, Jim is definitely wrong. You're not going to get credit for that. Home is definitely right. You're going to get credit for that. Went is not that wrong. It's just kind of different morphological form of the word to go. So maybe you should get partial credit. So we basically match if they have the same morphological root as them. Another one is synonyms, so walks and goes, so that requires some kind of repository of synonyms and says walking, going is, these are basically synonymous, so you still get partial credit for that. Okay, another way we can do this is using paraphrases, so if you basically match a paraphrase of the reference translation, you can also get partial credit for that. Here's a critique of automatic metrics, which is by no means comprehensive. That were raised, and they are raised frequently. One is that it ignores the relevance of words. So if you get a name or a core concept wrong, that actually should count as a bigger mistake than just having like a instead of the or other kind of function words. Or even you get penalized equally with punctuation. If you miss a comma in the middle, is as bad as missing a name. And that's a fair problem for certain applications. Certainly, names and core concepts are definitely much more important. Understanding, even information gisting, then is this person mentioned in the story is actually a much more important question than finer details about punctuation. They also operate on a local level, so look at words, and BLEU scores up to 4 grams, but they don't look at overall grammaticality of sentences and sentence meaning. So we don't actually get penalized for having a lot of n-grams right, but producing grammatical gibberish. And for a long time, machine translation was mostly producing grammatical gibberish, and nobody seemed to be too concerned about it. It's not entirely true, because if you have a grammatically correct sentence, it probably also has more 4 grams, right? So you do get credit for that. Another critique is scores are meaningless. That is a general critique. It's even worse for BLEU or any kind of reference corpus related metric, because it's measured similar to the reference, and that is very, who produced the reference, how literal is it, and what is the test set specifically. So if you say you have a BLEU score of 20 or BLEU score of 30, it's actually a completely meaningless statement because that score only counts for this particular test set for this particular language pair. So it doesn't say anything about this is a good translation system. You can't advertise it. My machine translation system produces BLEU scores of 35 and then claim it's a good machine translation system. That's a meaningless statement. Actually, another one is that human translators score really low on BLEU. And that has probably a lot to do with that human translators are not as literal. They take a little bit more freedom in the translation. And so if you have 2 human translators and compare their output, they vary actually quite more than a machine might vary, because machine will stick to the word choices. And then whenever the human translator that produced the reference translation also decided to be literal, it'll match them. And when the human uh, translator that produced the reference translation decided to be a bit more loose and mostly guided by fluency, well, both the machine and the human are gonna have a hard time matching that exactly. Okay, so one thing, we came up with these metrics and we made somewhat hand-wavy arguments if they're good or not, but uh, we haven't really answered the question, are they actually doing the right thing? So the metrics we have are low cost, tunable, consistent, but are they correct? And the answer, the way we answer this is to say, do they correlate with human judgment? So here's a famous chart um, on an earlier version of, or different version of the BLEU score, called the NIST score, and human judgment. So there's two kinds of human judgments here, the ones we introduced, fluency and adequacy. So here, human judgment, for instance, for this translation, for this machine translation system, all its translation on average were scored kind of minus 1.0. Oh wait, no, this is, yeah, minus 1.0 on the human judgment score in terms of fluency and adequacy. And the NIST score says also it's a minus 1.5. These are normalized numbers here. And you can see these actually line up pretty well on this diagonal here. So here are translations that the humans thought were crappy and the NIST score thought they were crappy. And here's a translation that the humans thought was great and the NIST score also thought was great. So this is how we evaluate automatic evaluation metrics. We gather human judgments and we measure correlation with human judgment. So this becomes the metrics task, the task of coming up with metrics, a nice supervised machine learning problem. Here's a bunch of human judgments. Can you just optimize correlation with them? Here's a way correlation can be computed. So you have two variables. You have the automatic score X and the human judgment Y. So you have for multiple systems, you have then the average automatic score and the average human score. And for another system, you have an average metric score and an average human score. And you basically compute then Pearson's correlation coefficient, where we sum over, how much does X differ from the mean and Y differ from the mean, multiply that, and then this gets normalized, where this is the mean overall automatic scores, or for this year, the mean overall human scores, and this is the variance here again. How much do they vary from each other? Okay, so this is a way to measure, to basically take how well things fit to this line and distill it down to a single number. So since this is a well-defined task with a agreed upon evaluation, there has been a lot of active development on new metrics, which is still going on. There are metrics that look at also syntactic similarity. Why don't we parse both the reference translation and human translation, compare the similarity, semantic equivalent, and attainment. A lot of recent work on word embeddings and sentence embeddings also plays into that. Metrics that just specifically measure reordering in addition to word accuracy. Metrics that can actually directly be trained, or why don't we just come up with a bunch of features that measure similarity and then just optimize them, and so on and so on. So we actually have evaluation campaigns on evaluation metrics that rank metrics, and then we measure how well the evaluations metrics are doing on evaluating. And one way to do this is the Pearson correlation coefficient, and there's even discussion about that. I just want to show you two outliers that kind of popped up over the years. There's this one here. So you have a bunch of systems, and yeah, it's somewhat aligned. It's definitely pretty much monotone. Any system ranked better by human score also than ranked better by the BLEU score, except for this one here. So what is this one? So this one is a bit of a cheating system where someone took machine translation output and then just had humans fix it up. So you just post-edited the human output. So humans didn't really like that because it was a much better translation, especially in terms of fluency. And probably also in terms of adequacy, because humans that can make sense of it then can rewrite it in the sentence that makes more sense. But the BLEU score didn't really appreciate that. It didn't really improve much in terms of BLEU. So yeah, so this kind of a translation, very fluent, done by humans, it's not really correlated with other stuff. Here's another example on statistical MT where we had like two different statistical MT systems that were on this curve. One SMT system was just trained on more data than the other one. And at that time, there were still rule-based systems out there, fairly competitive, that also got really high human scores. Not really that much worse than this SMT system, but the BLEU score really didn't give it high scores. So machine translation systems that kind of seem to be optimizing towards these scores, also getting more credit for getting the right word choices, getting the right vocabulary jargon, which rule-based systems may not be able to match. So where are we with automatic metrics? So automatic metrics are a central tool for system development. They're not fully suited for rank different types of machine translation system. So you saw an example of rule-based with statistical, and more recently came up with statistical versus neural, although there was not much of a difference. The discussion was also in statistical versus syntax-based, where syntax-based systems usually had better translations according to human judgment, which were not fully appreciated by things like the BLEU score. It's still an open challenge, and there's still a lot of activity. Some cynical take on that, though, is that there's a lot of new metrics being proposed all the time, and it has absolutely no impact on what people are actually doing. People still use the BLEU score and report on the BLEU score. Maybe that's a fault of machine translation researchers to adopt better metrics, but maybe also because the metrics are not that compellingly better. Okay, since we talk a lot about evaluation, this is also a good area to introduce statistical significance, because we might not only be interested in is system A better than system B, but is the difference statistically significant? Is it just some, I mean, they're just barely undistinguishable and just happened on this test that one is just slightly better than the other, but if you would take a different test set, it would be different. So is your improvement that you made to your system really significant, or is it just due to random noise? So that's something we should check for too. So here's the situation. You have a system A that has a particular score on the test set, and a system B that has another score on the test set. Same test set. And well, one system A in case is better than system B. So it has a higher score. So here's the question. Is system A really better than system B, or is it just some random fluctuation? If you would take two systems of equal quality on any given test set, one is going to be better than the other, ever so slightly. So is the difference in score statistically significant? So a core concept here, so there's something called a null hypothesis. This is the assumption that there's no real difference. Then there's something called p-levels that refers to the probability that there is a true difference. So this judgment of are these two systems actually different is never a clear yes/no judgment. There's always a measure of certainty associated with that judgment. And how certain you are in the judgment that system A is better than system B is measured in p-level. So p-level is this probability that the null hypothesis is true in a way, that there's no real difference. So if the p-level is smaller than 0.01, that means there's more than a 99% chance that the difference is real. And here are typical p-levels that are being used, 0.05, 0.01. Okay, another concept is confidence intervals. So if you give a measured score, what is a true score on an infinite size test set? So what is its true score? So this is just on a subset of the infinite size test set. So it's going to be a certain score. If I take a different subset, I'm going to get a different score. So what is the score in the limit if I take an infinite size test set? So we basically want to know this interval x minus d, x plus d, that contains the true score with 95% probability. Okay, here is an example. So you have 100 sentences that were translated, that were evaluated. 30 were found to be correct. So we have now a very simplistic human evaluation that's actually never used in practice, where we just say, is the sentence correct? Yes, no. What's the true translation score? So here you would say 30 divided by 100, so 30%, but that is true for these 100 sentences. But if you take different 100 sentences of the same kind, you might get 29 right, or 33, or who knows. So here's the idea, that this is how much you actually measured, and that's still your most probable guess of what the correct ratio of correct translations are, or correct score is. And then you have this bell curve, and you're interested in the area under the bell curve that covers 95%, which then gives you this interval. Okay, so this is a normal distribution here. So we basically want to compute the confidence interval for normal distributions. So here we have the mean and the variance. These are just the standard formulas for mean and variance. So this is the mean that we computed, and the question is, what is the true mean? So there's something called student's t-distribution that answers this question. So it's computed by this equation here. So you take the variance and divide it by the number of samples, and then there's also this constant t, or this variable t, that comes out of this table here. So it's a bit complicated to compute that, but there are tables where you can look that up. So if you test set sample of 100, 99% significance, so this is the numbers you're going to plug in there. Just go through our example here. So we have 100 sentences that were evaluated, 30 were found to be correct. So our sample mean is 30 out of 100, that's 0.3. The sample variance is, so some sentences were found correct and some weren't. So the variance here is 0.2121. So now we consult the table for 95% significance and a sample size of 100, and that gives us this number here. So where do we find this number here? 195. Here's the number, 1.9849. So that gives us this here, t times variance square root of sample size gives us 0.04. That tells us with 95% certainty the true score is in this range. So we found 30 correct, but anything between 26 and 34 would have also happened with 95% probability. So this gives us a confidence interval. We are usually not that interested in absolute scores, partly because they're not that meaningful. We are more interested in, is system A better than system B? mainly during the engineering phase, where if you change the system, you want to know, is it improvement? So I ran my system, BLEU score goes up by a fraction. Does that mean anything? So here's a simplistic setup. So you have a test set of 100 sentences. System A is better on 60 sentences. System B is better on 40 sentences. So you just basically have pairwise judgments, either by human judges or by your automatic scores. So A is better on 60 and B is better on 40. Is A really any better in general? Is that difference significant? Okay, so one way to test this is the sign test. So this is just the probability of this being the case by using a binomial distribution. So system A is better with the probability of P of A, and system B is better with the probability of P of B, which is 1 minus P of A. So we're ignoring ties here. And the probability of system A being better on K sentences out of a sample of N sentences. So that's just, given these probabilities, how likely is this case here? For instance, the system A is better on 60 sentences out of 100 sentences. How likely is a scenario possible? So that's just this binomial distribution. We just kind of repeat this experiment of picking a sentence. Probability A says 60%. Okay, we'll get that. So the null hypothesis is that they're the same. So that means P of A and P of B is 0.5. So if you put that in, and that simplifies this part here to just 0.5 to the power of n. So this gives you the probability of the null hypothesis. Okay, here's some examples. So this is the probability of the null hypothesis being right. So therefore the statistical significance, so this here would correspond to 95% statistical significance, because there's less than 5% chance that null hypothesis is right. If you only have 10 samples, then you really need to have one system A being better on 9 or 10 of the 10 sentences. So otherwise you can't say much. So you really need a larger sample. If you have 100, you still need to have system A being better on 61 of the sentences to say with 95% probability that's better. So the scenario where we only had 60 out of 100, system A being better, that's just passes this threshold here. So it's somewhere close to 90%, slightly over 90% certainty that system A is really better. For 99% probability, you need 64. So what you can see here, that the kind of ratios improve the bigger the test set. So one solution to this is always, if you want to have more statistically significant, have larger test sets. The larger the test sets, the more you can actually tell small differences apart. So what I just talked about had this simple metric of a system A being better than system B as a granular sentence level judgment, where you just had easy yes no decisions. But as I said, we now basically use machine translation metrics such as BLEU that are computed for the whole corpus, and they don't lend themselves to this kind of statistical analysis. And it's hard to get an analytical solution to this problem. So here is something called bootstrap resampling, which is a computational answer to the same question. So this is how it works. So you have a test set of, say, 2,000 sentences, and that is sampled from a large collection of sentences you could pull it from. So then you compute a BLEU score of this set, and that gives you a BLEU score. So if you repeat these two steps multiple times, let's say 1,000 times, each time you get a different BLEU score. You have 2,000 sentences, 2,000 sentences again, each time you get a different BLEU scores. So they're gonna differ a bit, but they're also gonna, have kind of a distribution where you get most of the BLEU scores kind of in the middle and then a few outliers. So if you then take away the here the you have 25 here, 25 here, and 950 in the middle, that corresponds then to a 95% confidence interval. Okay, so the only flaw with that is you have to have 1,000 times 2,000, ideally 2 million different sentences. Usually you don't have massive test sets like this. So what bootstrap resampling does is we sample from the same 2,000 sentences with replacement. So you might actually pick the same sentence multiple times. So again, you get different test sets each time and get different BLEU scores, except all these 2,000, these test sets are drawn from the same 2,000 sentences. The key here is with replacement, meaning you can pull the same sentence multiple times. And that there are mathematical reasons and empirical reasons why this actually also works. So you still only need to translate 2,000 sentences and then just do a lot of mathematical shenanigans afterwards to basically replicate this process. Okay, let me finish up with some other evaluation methods that have been proposed and are pursued. One big one is task-oriented evaluation. So machine translation is a means to an end. It's not really an end to itself. There's always something you want to do with the machine translated output. And the question is, does machine translation output help to accomplish the task? So here are two possible tasks that are pretty prominent. One is to use machine translation in a kind of a manual translation process where it's going to help you to produce high-level machine translations by just post-editing the machine translation output. And so you have human translators fix up the machine translation. Better machine translation should basically mean you have to fix less. Another one is information gathering from foreign language sources. So you have some material in foreign languages you don't understand. You want to find out, are they talking about this and what they're saying about this? So does the information come across? Here's post-editing machine translation. So you could measure the time that is being spent on producing translations. So the baseline is translation from scratch, and then post-editing, you check how much faster are they post-editing machine translations. So you measure the time for this here. Maybe they take on a particular corpus for the first one 20 hours. On the second one, they take 15 hours. So that then gives you an improvement of, 25% productivity improvement. This is fairly time consuming to do in practice, and one key thing, it also depends on the skills of the translator and post-editor. So if you actually look at the speed of translators, they vary quite a lot from each other. So some translators are just twice as fast, or 3 times as fast as other translators, which depends on skill or just generally effort and willingness to kind of pin down the kind of fine nuances or just moving on and being happy with good enough translations. So you have to normalize across translators. The problem is, of course, you can't have the same translator both translate from scratch and post-edit the same sentence, because if they see the sentence the second time, obviously they're going to be faster. There are metrics that are inspired by this task. One is called TER, which is based on the number of editing steps. So this sounds maybe familiar to what we said earlier, Levenshtein operations, insertion, deletion, substitutions, and we argued against it, except what they added was a penalty for movement. So if you have a big reordering, usually word error rate would have to account it with insertion, deletion, substitutions. translation edit rate just says this is one movement operation, and it costs you also as an error as much as one insertion, deletion, and substitution. It's actually computationally much more complex because of that. HTR is the human version of this translation edit rate that basically makes a human do these editing operations. So they're given the machine translation output, and they're basically doing post-editing in a way to correct the translation, and we measure how many things they change. So instead of measuring time, which we argued for here we measure how many editing steps were done. Another one is content understanding tests. So given machine translation output, can monolingual target side speaker answer questions about it? So what it then pins down to what are good questions to ask. So basic facts, who did this in this action, who bought the book, what was bought, and so on. So you can ask those kind of questions. You can ask about names, numbers, and dates. Also, you don't need to ask them. You can easily spot those probably automatically. You know, what are the relationships like? What did Mary did to John, and so on and so on. Or you can also be more fine-grained, nuance, and author intent, like, you know, given the story, was it important for Joe to do this and that? It's very hard to kind of devise these questions, and it's also very hard to find questions where machine translation, the differences in the quality of given set of machine translation systems makes a difference in answering these questions. Also, how much of these questions require a skilled human, and then how much does the skill of a human play a role. There was a sentence editing task that kind of explored this. So in difference to the post-editing task, so there are two people involved. One is someone editing the translation to make it fluent, except they didn't have access to the source or the reference. So they just give them, here's machine translated output. Can you tell me what it means, basically? Can you write it into a sentence that conveys the meaning or the intended meaning? Basically correct the fluency, but basically maintain as much adequacy as you can be spotted in there. And then the second person checks if this edited translation is correct. So then that is compared against the source. And if that is a correct translation now, after a human fixed it up without access to the source, it means that the first person actually understood what the meaning of the sentence was. So did person A actually understand the translation correctly? Okay, and that's it for today. There's, as I said, an endless debate about evaluation. There are also related topics that we didn't even cover today. One is called confidence estimation or quality estimation. So can we automatically provide alongside a machine translation system a confidence score about how confident the machine is in having the sentence translated correctly, which is also a very interesting topic. There's also kind of the application of these kind of quality evaluation methods to human translations. Can we check the work of human translators? And so on. So this is a kind of a wide open problem, and it's not going to be hard to find papers on this because this is a topic people love to engage in. Okay, and that's it for today, and I'll see you at the next lecture.